Welcome back, everyone. Ready for another deep dive? Today we're tackling something pretty mind-bending. Black hole thermodynamics.
Yeah, we're going to explore how scientists are using topology.
Topology, like the study of shapes.
Exactly. They're using it to understand these mysterious objects, black holes.
Okay, I'm intrigued, but I have to admit that sounds a bit abstract.
It is, but it's super fascinating. Our focus today is on a recent research paper.
Oh,
It's called Topological Insights into Black Hole Thermodynamics, Non-Extensive Entropy in CFT.
catchy title.
We'll break down this complex paper and highlight the most groundbreaking findings.
So we're talking about a paper that merges black holes with shapes. I'm in. But how do shapes help us understand black holes?
Okay, imagine trying to describe a complex dance move
Okay.
to someone who's never seen it before. You could try to explain the steps, the speed, even the angles,
Right.
but it wouldn't really capture the essence, would it?
No, not at all. You'd need to show them the whole sequence, the flow.
Yes, the shape of the movement.
I'm with you.
And that's exactly what topology brings to the table here. It lets us look at black hole thermodynamics, not just through numbers and equations, but through the shape of the processes involved.
So we're going beyond just crunching numbers.
Right. And this paper takes it a step further by applying topology to entropy, which is, well,
Entropy. That's a term I hear a lot, but honestly, I'm not always sure I fully get it.
I think a lot of people feel that way. It's a tricky concept, but think of it as a measure of disorder in a system. More entropy, more chaos, basically. Now, there's a famous formula, the Bekenstein-Hawking formula,
I've heard of that.
that describes black hole entropy. But physicists are now exploring newer, more nuanced ways of understanding entropy. They call these non-extensive entropies.
Non-extensive.
Yeah.
So it's like we're upgrading our understanding of entropy, moving beyond that classic model.
Exactly. These new entropies, they have names like Renyi, Sharma-Middle, and loop quantum gravity entropy. They offer a more detailed and, dare I say, a more exciting picture of how these systems work. They bring in new parameters that can really change how we interpret black hole behavior, like discovering hidden settings on the universe's control panel,
Ooh, I like that analogy. Okay, I'm hooked. So where does this topology thing come in with these new types of entropy?
Well, the paper focuses on a specific type of black hole, five-dimensional Gauss-Bonnet Ad-S black holes.
Okay.
Traditionally, scientists studied how these black holes change states, kind of like water changing from ice to liquid to gas by using free energy plots, but that can get really complicated.
Yeah, I can imagine the math getting pretty messy.
Totally. So that's where the topological method comes in. Instead of getting stuck in the equations, researchers can use a vector field and something called winding numbers to analyze those same transitions.
Okay, so it's like we're making a map of the shape of the transition instead of just plotting numbers on a graph.
Exactly, you got it.
So could we actually visualize these transitions in a new way then?
That's a great question, and researchers are looking into that. Now, this paper really digs into how these new entropies, combined with this topological approach, change how we understand those black hole phase transitions. And they start with something called Renyi entropy.
Renyi entropy. Tell me more. What's so special about it?
Well, Renyi entropy has this parameter, we call it Tl, that kind of tweaks how non-extensive it is. And what the researchers found is that below a certain critical value, it doesn't really matter, but above that value, whoa, choosing a different can completely change the black hole's phase transition.
Hold on. Are you saying there's this parameter that can drastically alter how black hole transitions from one state to another?
You got it.
That's incredible.
It is, and it suggests that even small changes in how we define entropy could change our predictions about how black holes evolve. It could rewrite our understanding of their entire life cycle.
Wow, this is blowing my mind a bit. So just by changing this view, we could see a black hole behave in completely different ways. It's like we have a control knob for black hole behavior.
It's a powerful concept, and the researchers didn't stop there. They also looked at another entropy called Sharma-Middle entropy.
More entropy, bring it on. What did they find out about Sharma-Middle entropy?
Get ready, because this is where it gets really interesting. So Sharma-Middle entropy, it adds another layer of complexity, and this is where the shape aspect of topology really comes in.
Okay.
It has two parameters, I and Vo, and they can change not just the phase transition itself, but also something called the topological charge.
Topological charge. Now that sounds like something straight out of science fiction. What is that?
Think of it as a unique fingerprint for the type of phase transition. It tells us about the specific characteristics of that change.
Okay, so it's not just about the black hole changing from one state to another.
Right.
It's about the specific way it transitions. Interesting. So how do these on values, how do they play into this?
Well, the fascinating thing is these on-bow values, they're like a cosmic recipe, only when you have the right combination. And another factor related to the black hole hits a certain level.
Oh, okay.
Then and only then do we see a very specific type of transition. We call it a first-order transition with a topological charge of +1.
So it's like baking a cake. You need the right ingredients in the right amounts to get that perfect fluffy result. But instead of flour and sugar, we're talking about these like cosmic parameters controlling black holes.
I love that analogy. And what makes this even more intriguing is that we're not just talking about some theoretical idea here. Remember the at CFT correspondence we talked about earlier?
Yeah, vaguely. Refreshing my memory.
Well, at space, that's theoretical, but CFTs. They're used to describe real systems like condensed matter and even some parts of particle physics.
Whoa, wait. So what we're learning from these like theoretical black holes could actually help us understand the physical world around us better.
Exactly. The best part about physics is that these seemingly abstract ideas, they often have surprising connections to real, tangible things. This research really shows that. Now, we can't talk about this without mentioning another type of entropy, loop quantum gravity entropy.
Loop quantum gravity entropy. Okay, that sounds intense. How is that different?
Loop quantum gravity, or LQG, it's basically a mind-blowing attempt to combine quantum mechanics and general relativity. It's trying to quantize space-time itself.
Well, hold on. Quantized spacetime. We're talking about the very fabric of reality here. So where does entropy fit in?
The researchers applied an entropy formula based on LQG to these black holes
Right.
and found that it, too, had a new parameter denoted as Q. And guess what? It could change the topological classification of the transitions again.
Another parameter to play with. What's crazy is that these different types of entropy, they each have their own unique parameters.
Yeah.
And they're all pointing to this way more complex picture of black holes than we ever thought before.
You got it. That's what makes this research so groundbreaking. It's challenging our assumptions and pushing us to explore new frontiers in how we understand the universe. This whole topological approach, it's revealing this hidden layer of complexity.
Right.
And it's making us ask questions we never even thought of before.
It's like we're peeling back layers of reality and discovering the universe is even more intricate than we ever imagined. So where does this all leave us? What are the big takeaways from all of this?
Well, one of the biggest implications is that how we think about black hole thermodynamics, it's changing drastically. These non-extensive entropies, they're not just theoretical anymore. They could completely change how we understand how black holes act and evolve.
So it's like we've upgraded our toolbox with these new entropies and the topological method, letting us see black holes in a whole new light.
Exactly. And remember, even though this research focuses on those theoretical black holes in five-dimensional ADS space, the implications go way beyond that. The add-SCFT correspondence hints at connections to real-world systems.
So these insights could, like, spill over into other areas of physics and lead to new discoveries and technologies.
Totally. Think about it. Imagine predicting and controlling how materials change states with incredible precision just by knowing the topology of their structure.
That's mind-blowing. So we could create materials with completely new properties by tweaking those hidden parameters.
That's the idea. The possibilities are pretty much endless. One thing that really stands out to me about all this is how it shows that seemingly different areas of physics are actually interconnected.
You mean like gravity, thermodynamics, and quantum mechanics all playing a role in how black holes behave?
Exactly. That's what makes studying black holes so captivating. They're not just isolated objects out there in space.
Right.
They're portals to understanding the fundamental laws that govern reality itself.
I love how this deep dive took us from abstract math to the very fabric of reality. What a wild ride. I feel like my brain is buzzing with new ideas.
Mine too. It's always exciting to explore these cutting-edge topics and see how they challenge us to think differently about the universe. But before we get too carried away, it's important to remember that this is still theoretical research. There's a lot we don't know, and these models we're using, they have limitations.
True. It's easy to get caught up in the excitement, but we have to stay grounded and keep pushing for more research to make sure these ideas hold up.
Absolutely. And that's what makes it all so exciting. There's always more to learn, explore, and more mysteries to unravel. Who knows what other secrets of the universe we can uncover through topology?
Now, that's a thought-provoking question.
Yeah.
Yeah, it really makes you wonder, like, what other parts of physics could benefit from this kind of topological approach? Are there other hidden connections just waiting to be discovered?
That's the beauty of science, right? Every new discovery leads to a whole bunch of new questions and possibilities. We're constantly expanding our knowledge, and who knows what we'll find next.
Speaking of new discoveries, one thing that stood out to me was how this research used a very specific type of black hole, a five-dimensional Gauss-Bonnet NS black hole. It sounds super complex and theoretical. So how does that connect to the black holes we actually observe in the real universe?
Great question. Theoretical physics often uses these idealized models to explore basic concepts in a simpler setting.
So it's kind of like setting up a controlled experiment in a lab,
Yeah,
even if it doesn't perfectly match the real world.
exactly. These five-dimensional black holes, we can't directly observe them, but they give us a testing ground for new ideas and mathematical frameworks. And then we can apply what we learn to more realistic black hole models.
So it's like a stepping stone to understanding the universe better, even if it's not a perfect picture of reality.
Exactly. It's like building a bridge between abstract math and the observable universe.
That makes sense. Like
Yeah.
using a simplified map to navigate a complex city. It might not have every detail, but it helps you understand the layout and find your way around.
Perfect analogy. Now, one thing to remember is that while this research shows the potential of topology and these non-expensive entropies, it's still an ongoing area of research. There are limitations, and there's a lot more work to do to really test these ideas and make sure we understand them fully.
So it's like having a rough draft of a map. It points us in the right direction, but there are still blank spots and areas to explore further.
Exactly. And that's what makes it so exciting for scientists. It's a frontier with tons of potential for new discoveries and insights.
I can definitely see why researchers are so fascinated by black holes. They're like a window into the biggest mysteries of the universe.
And that's one of the key takeaways from this whole deep dive. Black holes aren't just these weird objects far away in space. They're like labs for exploring the most fundamental laws of physics, the nature of reality itself. By using topology and these new entropy ideas, we're opening up a whole new world of possibilities for understanding these incredible objects and the universe they live in.
This has been an awesome journey. We've explored some seriously complex concepts, challenged our own assumptions, and gotten a glimpse of the potential for some groundbreaking discoveries. I don't know about you, but I'm feeling super inspired to keep learning and exploring the universe.
Me too. And to everyone listening, remember that learning is an adventure that never ends. Keep asking questions, keep challenging your assumptions, and keep diving deep into the mysteries of the cosmos.